In optimization theory, it's common to talk about first-order conditions and second-order conditions. The first-order condition for a maximum is simply that the first derivative be 0. Okay. If you have a function y equals f of x, a function of a single variable, then the first-order condition is said to be a necessary condition. And this first order condition is just f prime of x0 is equal to 0. And this is oftentimes referred to as a necessary condition. It's a condition that has to be satisfied in order for you to have either a maximum or a minimum. Okay. This is the first order condition for both a maximum and a minimum. Now, the second order condition, the second order sufficient condition for a maximum is that the second derivative be negative at the critical value of x. Okay. The second order sufficient condition for a minimum is that the second derivative be positive. Okay, so again, let's form a little table to illustrate these results. Let's write the conditions for a maximum and the conditions for a minimum. The first order conditions are the same. And these first order conditions are frequently said to be necessary conditions. They have to be satisfied. Technically, for you people who are math majors, we are assuming that the function is differentiable everywhere. So we're assuming that. So the necessary condition is that the first derivative be equal to 0. And this value of x sub 0 is called what? What is this value of x called? Where the first derivative is 0? The critical value. X sub 0 is the critical value of x. Okay. Now the second order conditions I'm going to talk about here are the second order sufficient conditions. Now, these sufficient conditions guarantee that you have either a maximum or a minimum if they're satisfied. Okay. For example, if the value of the second derivative is negative, the value of the second derivative at the critical value of x is negative, that guarantees that you have a relative maximum. And let me illustrate this as just a relative maximum. And this is just a relative minimum. The second order sufficient condition for a minimum is that the second derivative be positive at the critical value of x. Okay. All right. These second order sufficient conditions are conditions you look at after you've already found the critical value of x. after you've already satisfied the necessary first-order conditions. Okay. So this is really the tools. This is a table you use to help you to solve maximum and minimum problems. Okay. Let me give you a simple example. And this is kind of an interesting example. Mathematically, it's an interesting example. Consider this function right here. X plus 1 over x. Where, of course, we don't let x be 0. X can't be 0. Okay, because then 1 over x will be undefined. Okay, but this function's defined everywhere else. How would you go about finding the maximum or minimum of this function? I ask you, find the maximum or minimum values for this function. How would you proceed? All right, that's always what you do first, Jay. Take the first derivative, set it equal to 0. In this case, Jay, what is the first derivative?
1 minus x.
Exactly. And actually, it might be helpful if we just think of this function as being x plus x to the minus 1 power. Instead of writing it as 1 over x, think of it as being x to the minus 1. Then you just use a power function rule. And then the derivative is just as Jay said, 1 minus x to the minus 2 power. Okay, now that we found this derivative, Jay, what do we do with it? Set it equal to 0. Okay. And solve for x. So you get 1 equals x to the minus 2. Or if I just multiply both sides of this equation by x squared, I get x squared equals 1. And this equation really has 2 roots, doesn't it? What are the roots, Jay? Right, either plus or minus 1. So the 2 roots are, let's call them x1, comma x2, equals plus 1 and minus 1. Okay, plus or minus 1. Okay. Now, let's suppose we take this x equals plus 1. What do we have? Or let me just ask you, what's our next step, Jay? So actually, we found the critical values. In this case, there are 2 critical values. Not just 1, but 2 critical values. Where the first derivative is 0. What's my next step? Exactly. And what is the second derivative for this problem? What is f double prime of x? Okay. You bring that minus 2 down. The derivative of 1, of course, is 0. So you just differentiate this term. Bring that minus 2 down. So it's 2 times x to the minus 3. Okay. Now, what do we do with that?
Depending on what x values we're putting in, find out whether
Yeah. Okay. Okay.
Okay.
Right. So what x values do we want to look at in particular?
Plus and minus 1.
Exactly. So let's just choose plus 1. And let's look at the value of the second derivative at x equals 1. F double prime of 1 obviously is equal to 2 times 1 to the minus 3, or it's equal to 2. So What does that mean?
The second derivative is positive
Right.
at x is equal to 1, therefore 1 is local or relative.
Yes. Therefore, at x equals 1, you have a relative minimum. Right. Right. At x equals 1, you have a relative minimum. And the value, that minimum, is just going to be f of 1. So let's just say f of 1 is a relative minimum. Very good job, Jay. And f of 1 is, what is f of 1, by the way? 2. Yeah, just go back to here. 1 plus 1 over 1. 1 plus 1 is 2. So 2 is a relative minimum. Okay. 2 is a relative minimum. Okay. Let's look at the other one. The other critical value of x was minus 1. So what is f double prime of minus 1? Here's our f double prime of x. So at x equals minus 1, what is f double prime? Okay, just negative 2, because x minus 1 to the minus 3 power is the same thing as minus 1 cubed, which is a minus 1. So it's just going to be minus 2. Okay, let me just show you that. It's 2 times minus 1 to the minus 3. It's 2 over minus 1 cubed, which is just 2 over minus 1. Minus 2. Okay. All right. So that means f of minus 1 is what? F of minus 1 is, okay, it is equal to minus 2, right? F of minus 1 is equal to minus 2, and that is what? Yes, this is a relative maximum. But wait a second. Something is odd here, isn't it? What is odd? That's why I said this is an interesting mathematical problem. What's odd about this problem? Yes, the maximum is minus 2, and the minimum is 2. Now, how can that be? How can the maximum be smaller than the minimum? Yeah, I think we've done everything correctly. This table is correct. Well, what would be a good idea to help us understand what's going on? Who said that? Ben. Graph. Good idea. Let's see if we can graph this one. And this is another thing for which derivatives are very helpful. All right. Oh, notice that x equals 0, this is undefined. At x equals 0, really the function's discontinuous right there. But obviously at x equals 1, we could find a value. At x equals 1, we know f of 1 is equal to 2. So we have this value right here. And actually, let me redraw this. I need more space. because I want to consider this other quadrant too. All right, we know at x equals 1, y is equal to 2, so we're at this point right here. Now, and our function is to repeat Now, what happens as x approaches 0, but x is still positive? What happens to this term right here as x goes to 0, but x is still positive? The x gets smaller and smaller, so what happens to 1 over x? For example, if x is 1 over 1,000,000, what is x? Now, I mean, as x goes to 0, what is this? You need to learn this. What is the limit of 1 over x as x goes to 0? Infinity. Okay, for example, if x is 1 over 1,000,000, 1,000,000, 1 over 1,000,000, then 1 over x is going to be 1,000,000. So as x gets closer and closer to 0, this thing is blowing up. So it's blowing up. It's asymptotically approaching that vertical axis. Now we know already that that at x equals 1, we have a relative minimum. So we know the first derivative is 0 right here. Tangent line has a 0 slope. So this function looks like this. We have a relative minimum at x equals 1. Okay. First derivative, 0 here, but positive. So it means the positive second derivative? Positive second derivative at this point. Means that the first derivative is getting smaller. It goes from positive to 0 to positive here. A positive second derivative. Okay. It's getting bigger. It's going negative to 0 to positive about that point. Okay. So, but what about the other part? Suppose x is negative. Suppose x is negative. Then you have a whole different graph in this section down here. And the graph is going to look like this. We know, and let's just look at this. Take the limit of 1 over x as x approaches 0, but x is approaching 0 while remaining negative. So x is approaching 0 from the left instead of the right. Then what is the limit of 1 over x? For example, if x goes to minus 1 over 1,000,000, 1 over x is, negative infinity. The limit of this is negative infinity. So if x approaches 0 from the left, this is negative infinity. If x approaches 0 from the right, then it's positive infinity. Okay. So that means in this part over here, as x approaches 0 from the left, it's going to negative infinity. And where is your maximum? Your maximum is at minus 1. And this maximum is equal to minus 2. Okay, so the answer to this question is, how is the maximum greater than the minimum? It can be because of this discontinuity at x equals 0. That's why you get this strange result. But the minimum up here is 2. The maximum is minus 2. And in this case, the minimum is greater than the maximum. It's because of this discontinuity at x equals 0. That's why this occurs.